The vertical asymptote,
Now we want to talk
x
about
equals a, notice it's an
asymptotes.
equation, is a vertical asymptote of the function if at least one of the following occurs. One thing that is on this slide that's very important is a rational function of this form where g of x and h of x have no common factors. Because if they have common factors, then we can cancel those factors. And it does not create an asymptote. It actually creates what we call a hole. We won't be going over holes. Our vertical asymptotes, after we cancel out any common factors, is going to be where the denominator equals 0. Think of it like an open circle, but it's an open circle on a two-dimensional graph as opposed to a number line. Let's say x can't be 0, so we would make an open circle and it would look like this. And we know now x can't be 0. But here, I can't just put a circle because I have a two-dimensional graph. So I put this vertical line. What creates this vertical asymptote? Let's use a function 1 over x. Because 1 over x has a vertical asymptote. There's nothing to factor. There's nothing to cancel. I know that I have a vertical asymptote at x equals 0. 1 divided by 0 is undefined. I'm just going to draw this graph here to help explain what actually is happening with a vertical asymptote. I'm going to draw these numbers in. They're not going to be to scale. I'm going to call this 1, and I'm going to call this 1. If I graph f of x equals 1 over x, x is 1, 1 over 1 is 1, so I have this point out here. Let's get closer to what we say is our asymptote. And how I could draw this asymptote is with a dotted line. I have a dotted line here because I'm saying we have this vertical asymptote at x equals 0. When x equals 1/2, well, now I have 1 divided by 1/2. I keep change flip. So 1 times 2 equals 2. Now I know at 1/2, I have this point at 2. And now I'm not going to keep going slowly lower. I'm going to go more quickly lower. And here's where things are not going to be to scale. Here is 1/10. Just like the last one, 1/10 becomes 10. Let's make this 1 over 1,000. I have another point at 1,000, but there's my next point. Notice if I have 1 over 1,000,000, call it 10 to the 6th, that's going to be 1,000,000. And the closer I get to 0, the value is getting larger and larger. My graph, 1 over x, is starting to look like this. And the closer I get to 0, the bigger my number gets. 1 over 0, because what happens at 0, I don't know. This is undefined. But you can tell that as I get closer and closer to this asymptote, it's getting closer and closer, and it's just getting bigger and bigger, but it can never touch that asymptote, because if it touched it, it would be saying that this is defined somewhere. And I could do the same thing in the negative direction. That graph will go down at 0. I can see that this vertical asymptote breaks it in half. And I have 2 pieces to it. If you had a number line and you wanted to just graph 1 over x on the number line, x can be anything except 0. Notice that divides the number line into 2 pieces. That's why what we're looking for is anywhere the denominator equals 0. Find the vertical asymptotes. There could be none. So I have this function, and the first thing I do is I factor. If I factor this, well, the numerator doesn't factor, but the denominator factors into x plus 3 times x minus 2. Now, nothing cancels. I don't have any common factors, do I? That means my vertical asymptotes, and I'm just going to abbreviate it, VA, is where the denominator, x plus 3 equals 0, or x minus 2 equals 0, which means that I have vertical asymptotes at x equals -3 and x equals 2. If I wanted to put in these vertical asymptotes, I would have one at 2, I'd have one at -3, and they would just be these dotted lines, similar to an open circle on a number line. And those are the vertical asymptotes. This graph is going to be divided into 3 pieces. I'm going to have some part of the graph over here. I'm going to have some part of the graph between those 2 asymptotes, and I'm going to have some part of the graph over here. Let's find the vertical asymptote. The first thing we want to do is factor. We have f of x is equal to x over, and I can factor that the difference of squares, x plus 2 times x minus 2. There's nothing to cancel, so I have 2 vertical asymptotes, one at x equals 2 and one at x equals -2. I want to make sure that the denominator is not equal to 0. That means x plus 2 cannot equal 0, or x minus 2 cannot equal 0, which gives me 2 and -2. F of x is equal to x plus 2 over x squared minus 4. Look now at the denominator. You could factor that to x plus 2 times x minus 2. But we can clearly see here that x plus 2 over x plus 2 can cancel. It doesn't change the domain. The domain is still x cannot be 2 or x cannot be -2. And we could put this into interval notation if we wanted, but the vertical asymptote, we only have one at x equals +2, because all we worry about is the factor that's left. This creates what we call a hole, which we will not talk about in this class. Thank you for watching. Have a good one.